You know the word edge, you understand boundaries, the place where something ends and something else begins, the line between here and there. It feels simple, definite, clear. But when you apply this word to the universe itself, something changes. Because the universe doesn't have an edge in the way a table has an edge, or a country has a border, or even the way Earth has a surface. The universe's edge isn't a place you could travel to and touch. It isn't a wall. It isn't a boundary in space. It's a boundary in possibility itself. There is a limit to what you can see. There is a limit to what you can ever reach, even if you travelled forever. There is a limit to what you can know, measure, or verify. These limits aren't imposed by technology or human lifespan. They're woven into the structure of reality. They exist because of what the universe is, how it began, and what it has been doing ever since. This edge surrounds you right now. You exist inside it. Everything you've ever seen, every galaxy and every photograph, every distant quasar, every ancient light, all of it lies within this boundary. And beyond it, the universe continues. It must, but you will never see it. No telescope will ever capture it. No signal will ever cross it. No future civilization, no matter how advanced, will ever breach it. This isn't a story about where the universe ends. It's about where your relationship with the universe ends, where observation becomes impossible, where knowledge meets its absolute limit, where everything you can ever interact with, measure, or confirm stops, and the rest of existence continues without you, unreachable and unknowable forever. Let's begin with something simpler. Let's begin with light. Every day you move through spaces you consider empty, and you do so without giving them much thought. An unoccupied room, a quiet hallway late at night, a seat beside you that no one has taken yet. These spaces register almost instantly as nothing, and just as quickly they disappear from your awareness. They feel neutral, passive. They do not demand interpretation. They simply exist as places where something is not happening. This is the most basic way humans learn what emptiness means. When a room is empty, it still feels complete. It has walls that hold it together, a floor that supports you, a ceiling that closes it off. Light behaves predictably. Sound echoes in familiar ways. You can stand anywhere inside it and still feel oriented. You know where you are in relation to everything else. Even without furniture or people, the room feels contained and legible. Its emptiness is not a condition. It is a temporary state. You understand without thinking about it that the room could be filled at any moment. Someone could walk in, a chair could be placed in the center, music could start playing. The emptiness feels reversible, almost optional, like a setting that could be changed without effort. Because of that, it never feels threatening. Even when the empty space grows larger, the intuition remains intact. A warehouse with nothing inside it still feels manageable. An empty parking lot late at night may feel eerie, but not incomprehensible. You can still see the edges. You can still imagine walking from one side to the other. Your body knows how long that would take. Your mind knows that the emptiness is not fundamental. It is situational. The same logic applies outdoors. An open field may stretch farther than you can cross quickly, but it is still framed by a horizon. Trees, hills, buildings, or the curve of the land give it context. The sky above it provides orientation. Even if the field is silent, the silence feels local, not absolute. Wind moves, insects pass through. The emptiness is alive with small familiar activity. This is important because it reveals something subtle about how human intuition works. We do not define emptiness by what is missing. We define it by what remains. Walls remain, air remains, gravity remains. Time passes at a rate we recognize. Cause and effect still feel immediate. If you drop something in an empty room, it falls as expected. If you speak, your voice returns as an echo. The emptiness does not interfere with how the world behaves. So we learn, very early, that emptiness is cooperative. It does not resist us. It does not distort our actions. It does not demand patience. It allows us to move, speak, and act as though it were barely there. And because of that, we stop treating it as something real in its own right. This understanding extends naturally into how we experience time. A pause in conversation feels empty because it is brief and expected. A quiet moment in the middle of the day feels empty because it is surrounded by busier moments before and after. Even boredom, which we often describe as feeling like a void, is framed by the assumption that it will end. Something will eventually happen. Time will move on, and the emptiness will resolve itself. Human emptiness is always temporary. It is something you pass through, not something you remain inside. It exists between events, between objects, between actions. It is never the dominant condition. It is always the background. And because it is always bounded, we feel safe inside it. We know where it begins and where it ends. We know how long it will last. Even when we do not enjoy it, we trust it. The emptiness does not threaten our sense of control. We remain oriented in space and time. This trust becomes invisible. It settles so deeply into our thinking that we stop noticing it altogether. We begin to assume that emptiness, by its nature, is inert, that it does nothing unless something enters it, that it waits. But this assumption only holds because the emptiness we experience is small. Even the quietest room on Earth is full of things we do not consciously register. Air presses against your skin. Temperature gradients shift slowly across the space. Countless molecules move, collide, exchange energy. Sound waves bounce even when no one is listening. Light reflects off surfaces even when no one is watching. The emptiness feels empty because its activity does not matter to us. It does not affect our plans. It does not disrupt our expectations. It behaves in ways that align with our intuition, so we dismiss it as nothing. This is not a mistake. So we learn to collapse emptiness into irrelevance. We do this automatically. When you remember walking across an empty room, you do not remember the space itself. You remember entering and leaving. When you recall a quiet afternoon, you remember what came before and after, not the emptiness in the middle. The void, as we experience it, leaves almost no memory. This reinforces the idea that emptiness is not a thing. It is an absence of things. But even in human life, there are moments when this intuition begins to strain. Consider what happens when emptiness lasts longer than expected. A pause in conversation that stretches beyond comfort stops feeling neutral. It begins to feel heavy. Not because anything has happened, but because nothing has. The emptiness itself starts to carry meaning. Or consider standing alone in a large empty space with no immediate task. The lack of stimulation becomes noticeable. The silence feels louder. The space begins to press in on your awareness. The emptiness is still bounded, still temporary, but it is no longer invisible. These moments are rare, but they hint at something deeper. They suggest that emptiness is not inherently passive. It only feels passive when it is small enough, short enough, and structured enough to disappear into the background of our lives. The everyday empty we know is carefully shaped by limits. It has walls, it has horizons, it has timelines, it has expectations. It exists within systems that give it meaning without asking it to create meaning of its own. This is why we are so confident when we talk about nothing. We believe we understand it because we have spent our entire lives surrounded by controlled, cooperative absences. We believe that emptiness is simply what remains when you remove object, sound, or activity from a space. And at human scale, this belief works well enough, but it carries an unspoken assumption that emptiness depends on what surrounds it, that it borrows its behavior from nearby structure, that without context, it would have no character of its own. This assumption has never been tested in our daily lives. We have never known emptiness without nearby matter, nearby boundaries, nearby timescales that make sense to us. We have never lived inside an emptiness that stretches beyond immediate reference. We have never depended on emptiness itself as the environment, so when we imagine a void, we unknowingly shrink it. We imagine a larger room, a bigger field, a longer pause. We scale up our familiar emptiness and assume the rules remain the same. We assume it will still be passive, still temporary, still waiting. This is where the misunderstanding begins. What we call everyday empty is not a true absence. It is a local condition inside a dense, structured world. It is a convenience created by scale, not a fundamental state of reality. That difference feels subtle when we remain close to home. It feels almost semantic, a matter of definition rather than consequence. But once scale begins to grow beyond the boundaries that protect our intuition, emptiness stops behaving like a background and starts behaving like a condition. And when that happens, the word void no longer means what we thought it did. The idea of emptiness becomes more interesting when it stops being a place you stand in and starts being a distance you must cross. You flip a light switch and the room brightens. Instantly, it seems. The photons leave the bulb and strike your eye in a span of time too brief to measure without instruments. For all practical purposes, the light is just there, immediate, present. This is how light feels in everyday life. It doesn't travel. It simply exists where you need it. But light does travel. It moves at a fixed speed, roughly 300,000 kilometers per second, and every photon that reaches your eye has made a journey to get there. The light from the bulb crosses the room in about 10 nanoseconds. The light from the sun crosses 150 million kilometers of empty space in 8 minutes and 20 seconds. The light from Alpha Centauri, the nearest star system, crosses 4.3 light-years, arriving more than 4 years after it was emitted. This means that when you see something, you are not seeing it as it is now. You are seeing it as it was when the light left it. The sun you see in the sky is the sun as it existed 8 minutes ago. Alpha Centauri is the star as it was 4 years ago. The Andromeda Galaxy, visible as a faint smudge in a dark sky, is the galaxy as it existed 2.5 million years ago, during the time when early human ancestors were beginning to use stone tools on Earth. For nearby objects, this delay is irrelevant. 8 minutes is negligible when discussing the sun. Even 4 years is inconsequential on human timescales. But as distances grow, the delay becomes significant. 10,000 light-years means 10,000 years into the past. 1 million light-years means 1 million years. 1 billion light-years means 1 billion years. The light you see from distant galaxies is ancient light, emitted long before Earth existed, travelling through expanding space for eons before finally arriving at a detector pointed in the right direction at the right time. This transforms astronomy into a form of archaeology. When you observe a distant galaxy, you are not studying its current state. You're studying its history. The stars you see in that galaxy may have already died. The galaxy itself may have collided with another, merged and changed entirely. Or it may look almost exactly the same, relatively unchanged over billions of years. You cannot know. You can only see what the light tells you, and the light is old. The most distant galaxies we have observed are more than 13 billion light-years away. The light from these galaxies has been travelling since the universe was only a few 100 million years old, less than 5% of its current age. These galaxies are not distant in the way that another country is distant. They are distant in time. You're seeing them as they were in the ancient past, in an era when the universe was younger, hotter, smaller, and fundamentally different from what it is today. This creates a strange relationship between distance and time. In everyday life, these two concepts are separate. Distance is space, time is duration, but in cosmology they merge. To say that a galaxy is 13 billion light-years away is to say that its light has been travelling for 13 billion years. Distance becomes a measure of time. The further something is, the older the light. The deeper you look into space, the further you look into the past. And this is not a metaphor, it is literal. The photons reaching your telescope right now from a distant galaxy left that galaxy billions of years ago. They have been travelling through space ever since, crossing unimaginable distances, moving at the maximum speed that anything can move, and they are only now arriving. Each photon is a messenger from the past, carrying information about conditions that existed long ago, in a place that may no longer resemble what the photon represents. Consider what this means for observation. When you look at a galaxy 1 billion light-years away, you see it as it was 1 billion years ago. When you look at a galaxy 2 billion light-years away, you see it as it was 2 billion years ago. When you look in different directions at galaxies at different distances, you're seeing different moments in cosmic history all at once. The universe you observe is not a single snapshot in time. It is a patchwork of different eras, stitched together by the varying travel times of the light. The night sky is a time machine, not in the science fiction sense where you travel backward or forward through time, but in the sense that the light reaching you has travelled through time to get here, and by observing it, you are witnessing events that happened in the distant past. You're looking at history. The further you look, the deeper into history you go, until you approach the very beginning of observable time itself. There is a limit to how far back you can see, not because the universe stops, but because there is a point beyond which light cannot travel. In the earliest moments after the Big Bang, the universe was so hot and dense that photons could not move freely. They were constantly absorbed and re-emitted by charged particles, trapped in a thick plasma that was opaque to light. This era, called the photon epoch, lasted for roughly 380,000 years after the beginning. Then, as the universe expanded and cooled, a transition occurred. The temperature dropped enough for electrons and protons to combine into neutral hydrogen atoms. This process, called recombination, rendered the universe transparent. Photons were no longer trapped. They could travel freely through space, and the light emitted at that moment, the moment of recombination, has been travelling ever since. It is the oldest light in the universe, the most ancient signal we can detect. This light is called the cosmic microwave background, or CMB. It fills the entire sky. Every direction you look, you can detect it, a faint glow of microwave radiation, left over from the moment the universe became transparent. The CMB is not a distant object, it is a boundary, a surface of last scattering, representing the furthest back in time we can see with the light. Beyond it, the universe was opaque. No photons from that earlier era can reach us. The CMB is the edge of the visible past. When you observe the CMB, you're seeing light that has been travelling for more than 13 billion years. But here is where things become strange. The source of that light, the region of space where those photons were emitted, is not 13 billion light years away. It is much further, roughly 46 billion light years away in fact. How is this possible? How can light that has been travelling for 13 billion years come from a source that is 46 billion light years distant? The answer is expansion. The universe has been expanding the entire time the light was travelling. The photons were emitted from a region of space that was much closer to us when they were released. But as they travelled toward us, space itself stretched, carrying that region further away. The photons were swimming upstream, so to speak, moving through a medium that was itself expanding. They still travelled at the speed of light, covering 300,000 kilometres every second. But the destination they were aiming for kept moving away. By the time those photons reached us, the region of space they came from had been carried away by expansion to a distance of 46 billion light years. The light is 13 billion years old, but the source is 46 billion light years away. Distance and time are no longer proportional. The expansion of space has decoupled them. This changes how we think about cosmic distance. In a static universe, distance would simply be the speed of light multiplied by the travel time. If light has been travelling for 1 billion years, the source would be 1 billion light years away. Simple, linear. But the universe is not static, it is expanding, and this expansion stretches the space between the source and the observer even as the light is in transit. This means that the distance to a distant galaxy is not a single, fixed number. There is the distance the light has travelled, measured in light years of time. There is the comoving distance, which accounts for expansion and tells you how far away the galaxy is now, at this moment. And there is the proper distance, which tells you how far away the galaxy was when the light was emitted. All three are different, all three are valid, and all three depend on how you account for the expansion of space. Light, then, is not just a signal, it is a record, a fossil. Each photon carries information not only about the object that emitted it, but about the journey it took to reach you. The wavelength of the light tells you about the expansion of space during transit. Photons from distant galaxies are redshifted, stretched to longer wavelengths by the expansion. Their colours shifted toward the red end of the spectrum. The more distant the galaxy, the greater the redshift, and the faster the space between us and it has been expanding. This redshift is measurable, precise. It allows astronomers to determine not just how far away a galaxy is, but how fast the universe was expanding when the light was emitted, and how much space has stretched since then. The light becomes a ruler, a clock, and a historical document all at once. Every photon is evidence. Every observation is a look into the past. But this creates a problem, because if light takes time to travel, and the universe is expanding while it travels, then there are regions of space from which light has not yet had time to reach us. And there are regions of space from which light will never reach us, because the expansion is too fast. The journey is too long. The gap is unbridgeable. You're not seeing the universe as it is. You're seeing the universe as it was across a range of different times, all layered together in your observation. And the further you look, the older the image, until you reach the edge of what light can show you. Beyond that edge, there is no light, no signal, no information, just space, continuing unknowable and invisible, forever out of reach. Imagine holding two objects in your hands, one in each palm, a meter apart. Now imagine moving your hands further apart. The objects separate. The distance between them grows. This is motion. One object moves away from the other through space. Simple, intuitive, the kind of movement you've experienced your entire life. Now imagine something different. Imagine that the objects don't move at all. Your hands stay perfectly still, but the space between them stretches. The meter of distance becomes 2 meters, then 3, then 10, without either object changing position. The space itself expands, not the objects moving through space, but space growing between them. This feels wrong. Space isn't supposed to do that. Space is the stage, the container, the fixed background against which things move. It doesn't stretch or shrink or change. It just is. And yet, this is exactly what the universe does. Space itself is expanding, not the galaxies moving away from each other through a static void, but the fabric of space growing, carrying galaxies along with it as it stretches. This concept is difficult to grasp because it has no analogue in everyday experience. You have never watched space expand. You have never felt it stretch. The expansion occurs on scales so vast that it's irrelevant to anything in your immediate environment. The distance between you and the wall is not growing. The distance between Earth and the Sun is not growing. Even the distance between our galaxy and the nearest galaxy is barely affected. Expansion only becomes significant across millions and billions of light years, distances so large that they exceed anything you could personally relate to. But at those scales, expansion dominates. Galaxies that are sufficiently far apart are moving away from each other, not because they're travelling through space, but because the space between them is increasing. And the further apart they are, the faster they recede. Double the distance and you double the recession speed. Triple the distance and you triple the speed. This relationship is linear, predictable, and it has a name: Hubble's law. Hubble's law states that the velocity at which a galaxy recedes from us is proportional to its distance. The constant of proportionality is called the Hubble constant, and it describes the rate of expansion. Currently, the Hubble constant is approximately 70 kilometers per second per megaparsec. This means that for every megaparsec of distance, roughly 3.3 million light years, a galaxy recedes at an additional 70 kilometers per second. A galaxy 10 megaparsec away recedes at 700 kilometers per second. A galaxy 100 megaparsec away recedes at 7,000 kilometers per second. A galaxy 1,000 megaparsec away recedes at 70,000 kilometers per second, and so on. The further away the galaxy, the faster it recedes, not because it's moving faster through space, but because there is more space between us and it, and all of that space is expanding. This creates a strange situation. Because there is no upper limit to distance, there is no upper limit to recession velocity. At some distance, galaxies recede at speeds approaching the speed of light. And at even greater distances, they recede faster than light. Not because they're violating relativity, but because the recession is not motion through space. It's the expansion of space itself. Relativity limits how fast objects can move through space, but it does not limit how fast space itself can expand. This is where intuition begins to fail. You understand motion, you understand speed, but you don't have a framework for understanding space as something dynamic, something that grows. And the implications of this growth are profound because they change what it means for something to be reachable. In a static universe, if you wanted to reach a distant galaxy, you would simply travel toward it. The distance might be vast, but it would be fixed. Every meter you travelled would bring you 1 meter closer. Eventually, given enough time, you would arrive. But in an expanding universe, the situation is different, because while you're travelling toward the galaxy, the space between you and it is growing. You're moving forward, but the destination is moving away, and if the expansion is fast enough, you can travel forever and never arrive. Consider a galaxy currently 10 billion light years away. If you could travel at the speed of light heading directly toward it, you might think you would reach it in 10 billion years. But you wouldn't, because during those 10 billion years, the space between you and the galaxy would continue expanding. The galaxy would be further away when you arrived than it was when you started. You would be moving toward it at the maximum possible speed, and it would still be receding from you. In fact, for galaxies beyond a certain distance, even light cannot catch up. A photon emitted from Earth, travelling toward a distant galaxy, will spend eternity crossing the expanding space between here and there. It will never arrive. The gap grows faster than the photon can close it. This is not a theoretical limit, it's a geometric fact. There are galaxies visible to us right now whose light we can detect, but which we could never reach, even if we travelled at the speed of light for the entire future history of the universe. This introduces a new kind of boundary. Not a boundary in space, but a boundary in causality. There are regions of the universe with which we can exchange information now because their light can still reach us. And there are regions with which we cannot exchange information because the expansion is too fast. The dividing line between these regions is not fixed. It shifts as the expansion rate changes. And crucially, the expansion rate is not constant. It's accelerating. This acceleration was discovered in the late 1990s when astronomers studying distant supernovae realized that the universe's expansion was speeding up, not slowing down. This was unexpected. Gravity should slow expansion. The mutual gravitational attraction between all the matter in the universe should be pulling everything back together, or at least slowing the separation. But instead, the expansion was accelerating, driven by something called dark energy, a mysterious component of the universe that exerts a kind of repulsive pressure, pushing space to expand faster over time. Dark energy changes everything. In a universe dominated by matter and gravity, expansion slows over time. Distant galaxies recede, but the recession slows. Given enough time, light from even very distant galaxies would eventually reach us. The observable universe would grow, slowly incorporating more and more of the cosmos as light from further regions finally arrived. But in a universe dominated by dark energy, expansion accelerates. The recession speeds up, and galaxies that are currently visible will eventually recede so fast that their light can no longer reach us. They will cross a boundary and disappear from view forever. This is happening now. Not quickly enough to notice in a human lifetime, or even in the entire span of human civilization. But over billions of years, galaxies at the edge of the observable universe are fading. Their light, already stretched to extreme redshifts, is being stretched further and further, dimming, cooling, until it becomes undetectable. These galaxies are slipping over the horizon, leaving the observable universe, not because they're being destroyed, but because the expansion of space is carrying them away faster than their light can reach us. The universe, you can see, is shrinking in a sense, not in physical size, but in content. The number of galaxies within the observable universe is decreasing. The sphere of visibility is not expanding outward to include more of the cosmos, it's contracting inward, losing galaxies to the accelerating expansion. And this process is irreversible. Once a galaxy crosses the boundary and its light can no longer reach us, it's gone, permanently. No future technology will bring it back. No improvement in telescopes will reveal it. It has left the observable universe forever. This creates a troubling picture. The universe is not a static stage on which events unfold. It's a dynamic, evolving structure, and the evolution is carrying most of it away from us. The galaxies we can see today represent a temporary collection, a snapshot of what happens to be within reach at this particular moment in cosmic history. In the past, we could see less. In the future, we will see less again. The observable universe is a bubble, and the contents of that bubble are changing, not because the universe itself is changing, but because the relationship between us and the rest of the cosmos is shifting as space expands. And here's the unsettling part. This expansion doesn't have a center. It's not as if galaxies are flying away from a central point, like debris from an explosion. Every point in space is expanding away from every other point. From our perspective, it looks like everything is moving away from us. But from the perspective of an observer in a distant galaxy, it looks like everything is moving away from them. There is no preferred location, no central origin. Expansion is happening everywhere, uniformly in all directions all the time. This means that the edge we're discussing, the boundary of the observable universe, is not a universal edge. It's specific to us. An observer in a distant galaxy would have their own observable universe, their own horizon, their own set of galaxies they can see and cannot see. Those two observable universes would overlap, but they would not be identical. There would be galaxies visible to them that are not visible to us, and vice versa. The universe is filled with these overlapping bubbles of observability, each centered on a different location, each defining a different collection of reachable and unreachable regions. You exist inside one of these bubbles. Everything you can see, everything you can measure, everything you can interact with or confirm the existence of lies within it. And the boundary of this bubble is defined not by walls or barriers, but by the expansion of space itself. It is the distance at which space expands so fast that light cannot cross it. It is the limit of causality, the edge of the knowable, and it is closing in. There is a distance in the universe where everything changes, not a physical place, not a structure you could visit or a landmark you could identify, just a threshold, a line drawn by mathematics and expansion. On one side of this line, galaxies recede slower than the speed of light. On the other side, they recede faster. This boundary is the Hubble sphere. The Hubble sphere sits at roughly 14 billion light-years away in terms of light travel distance, though its exact location depends on how you measure distance in an expanding universe. What matters is not the precise number, but what the boundary represents. It marks the distance at which the cumulative expansion of space equals the speed of light. Every megaparsec of space contributes a small amount of recession velocity, and when you add up enough megaparsecs, the total recession velocity reaches light speed. That's the Hubble sphere. Inside this sphere, recession velocities are subluminal. A galaxy 1 billion light-years away recedes at perhaps 70,000 kilometers per second, fast by any human standard, but still well below the speed of light. A galaxy 10 billion light-years away recedes faster, maybe 200,000 kilometers per second, closer to light speed but still beneath it. But at 14 billion light-years, recession velocity equals light speed exactly, and beyond that, it exceeds it. This creates a division in the universe, not between matter and void or between order and chaos, but between regions where light can make progress toward you and regions where it cannot. A photon emitted from a galaxy inside the Hubble sphere, travelling toward Earth, will eventually arrive. It might take billions of years. The photon might be stretched and redshifted by expansion along the way. But it's moving through space faster than space is expanding between here and there, so over time, it closes the gap. Progress is slow, but it's real. A photon emitted from a galaxy outside the Hubble sphere, heading toward Earth, will not arrive, not ever. It will travel at the speed of light, moving through space as fast as anything can move, but the space between the photon and Earth is expanding faster than the photon can cross it. The photon makes no progress. It's running on a treadmill that's moving backward faster than it can run forward. The distance to Earth increases even as the photon moves toward it. The journey is futile, eternal. The photon will never reach its destination. This sounds like it should define the edge of what we can see. If light from beyond the Hubble sphere cannot reach us, then the Hubble sphere should be the boundary of the observable universe. But it's not, because the Hubble sphere is not static. It's moving, expanding outward as the universe evolves. And a photon that starts its journey outside the Hubble sphere can find itself inside the sphere later, once the sphere has grown large enough to encompass it. Consider a photon emitted 13 billion years ago from a galaxy that was, at the time, outside the Hubble sphere. The photon heads toward Earth, moving at light speed but making no net progress because space is expanding too fast. For millions or even billions of years, the photon travels without getting any closer. It's stuck in a region where expansion dominates. But over time, the universe evolves. The expansion rate changes. The Hubble sphere grows, and eventually the Hubble sphere expands past the photon. Suddenly, the photon is inside the sphere. Recession velocity at its location is now less than light speed. The photon begins making progress. It starts closing the distance to Earth, and after billions more years of travel, it finally arrives. This is why we can see galaxies that are currently receding faster than light. Their light was emitted long ago when they were outside the Hubble sphere, but the sphere expanded, encompassed the light, and allowed it to make progress toward us. We're seeing ancient light from galaxies that have since moved beyond our causal reach. The photons are relics, fossils of a time when the universe was smaller, denser, and structured differently. The Hubble sphere, then, is not a barrier to observation, it's a barrier to communication. You can see things beyond it, as long as their light was emitted early enough and the sphere expanded enough to let that light eventually reach you. But you cannot send a signal to them. A photon leaving Earth now, heading toward a galaxy currently outside the Hubble sphere, will never arrive. Even if the Hubble sphere continues to expand, even if it eventually grows large enough to encompass that galaxy, the photon won't benefit, because by the time the sphere reaches the galaxy, the photon will be even further behind. Expansion is accelerating, the treadmill is speeding up, and a photon that starts outside the sphere today has no chance of ever getting inside. This asymmetry defines the Hubble sphere's role in cosmology. It's not the edge of visibility, it's the edge of influence. You can observe beyond it, but you cannot affect anything beyond it. You can receive information from regions outside the Hubble sphere, but you cannot send information to them. The sphere divides the universe into parts you can interact with and parts you cannot, and that division is permanent. And the sphere is growing, but not fast enough. In a universe dominated by matter, where expansion is slowing over time, the Hubble sphere would expand rapidly, eventually encompassing more and more of the cosmos. Galaxies would fall into it. The sphere would grow larger than the observable universe, and in principle you could send signals to anything you could see. But this universe is not dominated by matter, it's dominated by dark energy. Expansion is accelerating. And in an accelerating universe, the Hubble sphere expands, but the observable universe expands faster. The sphere is always catching up but never quite overtaking. What this means is that there are galaxies you can see right now whose light reached you, but which you could never signal. They're visible, but unreachable. Their light made it here because it was emitted long ago, before acceleration became dominant, when the Hubble sphere was positioned differently. But a signal sent from Earth today, heading toward those galaxies, will never arrive. The galaxies are already too far away. The expansion between here and there is already too fast. They exist on the other side of a one-way boundary. The Hubble sphere is moving outward, but the galaxies are moving outward faster. The gap between what you can see and what you can reach is widening. Over time, more and more galaxies will cross from the reachable category into the visible but unreachable category. And eventually, as expansion continues and accelerates further, galaxies will cross from the visible but unreachable category into the invisible and unreachable category. They will fade from view entirely, their light will stop reaching us, and they will be gone, not destroyed, but simply removed from the set of things we can observe, measure, or confirm. The Hubble sphere is not the edge of the universe. It's not even the edge of the observable universe. But it is an edge, a boundary of interaction, a line separating the parts of reality you can influence from the parts you cannot. And as the universe expands and accelerates, that line is shifting slowly but inevitably, reducing the portion of the cosmos you can ever hope to reach. There is a limit to how far back you can see, not because the universe stops at some point in the past, but because there is a beginning, a moment before which there was no space, no time, no light to observe. The universe has a finite age, roughly 13.8 billion years, and this age imposes a constraint on observation. Light travels at a fixed speed, and it has only had a finite amount of time to reach you. This creates a boundary, a horizon beyond which no light has had time to arrive. This boundary is called the particle horizon. The particle horizon is different from the Hubble sphere. The Hubble sphere marks the distance where recession velocity equals light speed right now, at this moment in cosmic history. The particle horizon marks the distance to the furthest regions from which light has ever reached us, accounting for the entire history of the universe. It's not about current recession velocity, it's about travel time, about whether a photon, emitted at the earliest possible moment, has had enough time to cross the expanding space and arrive here. In a static universe, calculating this distance would be simple. Light travels at 300,000 kilometers per second. The universe is 13.8 billion years old. Multiply the speed by the time, and you get roughly 13.8 billion light years. That would be the particle horizon, the furthest light could possibly have traveled. But the universe is not static, it's expanding, and expansion changes everything. When a photon is emitted from a distant source and begins traveling toward you, The space between the source and you is expanding. The photon is moving through that expanding space, crossing it at the speed of light. But while the photon is in transit, space continues to stretch. The distance the photon has to cover keeps growing. The photon still travels at light speed, but it's travelling through a medium that is itself expanding, and this affects how far the photon can get in a given amount of time. In the early universe, expansion was faster than it is now. The universe was denser, hotter, and the rate of expansion was much higher. A photon emitted shortly after the Big Bang had to contend with rapid expansion, space stretching aggressively, making progress difficult. But over time, as the universe expanded and cooled, the expansion rate slowed. Matter and radiation became less dense, their gravitational influence weakened, and the photon found it easier to make progress, to close the gap between its starting point and its destination. This means that a photon emitted 13.8 billion years ago has not travelled exactly 13.8 billion light years. It has travelled less in terms of the distance it covered through space, because space was expanding while it travelled. But the source of that photon, the region of space where it was emitted, is now much further away than 13.8 billion light years, because that region has been carried away by expansion during the time the photon was in transit. The current distance to the particle horizon, accounting for expansion, is roughly 46 billion light years. This is the comoving distance to the furthest regions from which light has reached us. The light from these regions was emitted when the universe was very young, only a few 100,000 years old. It has been travelling for more than 13 billion years, and during that time the space it came from has been stretched by expansion to a distance of 46 billion light years. The particle horizon defines the observable universe. Everything within this boundary, everything closer than 46 billion light years in comoving distance, is in principle observable. Light from these regions has had time to reach us. We may not have detected all of it. Our telescopes may not be sensitive enough to capture every photon, but the light is out there, travelling through space, and it could be detected if we built the right instruments and looked in the right directions. Everything beyond the particle horizon is unobservable, not because it doesn't exist, but because light from those regions has not had time to reach us yet. The universe is only 13.8 billion years old. Light travels at a finite speed. There is a maximum distance that light could have covered in that time, accounting for expansion. Beyond that distance, no signal has reached us. No information has arrived. No photon, no gravitational wave, no particle of any kind from those regions has ever interacted with anything in our observable universe. This creates a hard boundary. The particle horizon is not like the Hubble sphere, which shifts as expansion evolves. The particle horizon also moves, but in a different way. It expands outward as the universe ages, because every passing moment adds more time for light to travel. A photon that was just outside the horizon a billion years ago is now inside it, because it has had an additional billion years to make progress toward us. The horizon is always growing, slowly incorporating more of the universe as light from further regions finally arrives, but the rate at which the particle horizon expands is slowing. In the early universe, when expansion was decelerating, the particle horizon grew quickly. New regions came into view rapidly as light from further distances managed to reach us. But now, with expansion accelerating due to dark energy, the particle horizon is growing more slowly. The acceleration works against the light, making it harder for photons from distant regions to close the gap. The horizon is still expanding, but each additional year of cosmic time brings fewer new regions into view. And there's a limit. In an accelerating universe, the particle horizon does not expand forever. It asymptotically approaches a maximum size. There is a furthest distance that light will ever be able to reach us from, no matter how long we wait. Beyond that distance, expansion is too fast. Space is stretching too aggressively. Photons from those regions will never make it here. They will spend eternity trying to cross the gap, and the gap will always grow faster than they can close it. This maximum size is larger than the current particle horizon, but not infinitely larger. It's a finite boundary, set by the balance between the speed of light and the acceleration of expansion, and it defines the ultimate observable universe. Not what we can see now, but what we could ever see, given infinite time and perfect instruments. Everything within this ultimate boundary will eventually send light that reaches us. Everything beyond it will not. The particle horizon, then, is the edge of your cosmic past. It marks the furthest regions from which information has reached you. It defines the limit of what you can currently know about the universe based on observation. And as the universe ages, this boundary expands, revealing more of the cosmos, allowing you to see deeper into space and further into the past. But the expansion is slowing. The horizon is approaching its limit. And most of the universe, the vast majority of space, lies beyond this limit. There are galaxies out there, uncountable numbers of them, whose light will never reach us. Not because they're too faint, not because they're obscured, but because they are simply too far away and expansion is too fast, and the geometry of space-time does not permit their light to ever cross the distance between there and here. You exist inside a sphere defined by the particle horizon. Everything you have ever observed lies within it, and everything beyond it is, and will always be, invisible. The particle horizon tells you what you can see. It marks the boundary of the observable universe, the furthest distance from which light has had time to reach you since the beginning. But there is another horizon, subtly different, more absolute in its implications. This is the event horizon, and it tells you not what you can see, but what you can ever reach. In an expanding universe, these two concepts diverge. You can observe things you cannot reach. You can see galaxies whose light arrived here after travelling for billions of years, but which you could never visit, never signal, never interact with, even if you had infinite time and travelled at the speed of light. The event horizon defines this boundary. It separates the regions of space you could theoretically reach from the regions you could not, no matter what you do. Imagine sending a beam of light from Earth right now, directed toward a distant galaxy. The light travels outward at 300,000 kilometers per second, the fastest speed possible. But the space between Earth and that galaxy is expanding. As the light travels, more space is created in front of it. The light is making progress, covering distance, but the destination is moving away. Whether the light ever reaches the galaxy depends on a simple question. Can the light cross the expanding space faster than the space itself is growing? For nearby galaxies, the answer is yes. The expansion between here and there is slow enough that light can overcome it. The photon will take a long time to arrive, far longer than the current distance would suggest, because it has to fight against expansion the entire way. But eventually it will get there. The galaxy is within the event horizon. For distant galaxies, the answer is no. The expansion is too fast. The space between here and there is growing faster than light can cross it. The photon will travel forever, moving outward at light speed, covering more and more distance, but the gap to the galaxy will only widen. The photon will never arrive. The galaxy is beyond the event horizon. The event horizon is closer than the particle horizon, much closer. The particle horizon sits at roughly 46 billion light-years, marking the edge of what we can currently observe. The event horizon sits at roughly 16 billion light-years, marking the edge of what we could ever reach. This means there is a vast region of space, roughly 30 billion light-years deep, filled with galaxies we can see but cannot reach. We can observe their light. We can study their properties. We can watch them evolve over billions of years, but we can never send a signal to them. We can never visit them. We can never interact with them in any causal way. These galaxies are visible ghosts. Their light reached us because it was emitted long ago, when they were closer, when the expansion rate was different, when the geometry of space-time allowed photons to make progress toward us. But the galaxies have since moved beyond the event horizon. They are receding faster than light can travel, and a photon leaving Earth now heading in their direction will never catch up. This asymmetry is permanent. The event horizon is not expanding fast enough to catch these galaxies. In a universe where expansion is accelerating, the event horizon grows, but slowly, and it grows more slowly over time. The galaxies, meanwhile, are being carried away by expansion, moving further out, crossing into regions where the cumulative effect of expansion exceeds the ability of light to make progress. They are leaving the reachable universe, and they are not coming back. The event horizon is a cosmological point of no return. Once a galaxy crosses it, moving from inside to outside, it is lost to us. We can still see it for a while, because the light it emitted before crossing the horizon is still in transit, still making its way toward us. But that light will eventually run out. The galaxy will fade. Its image will redshift into invisibility, and then it will be gone. Not just from our ability to reach, but from our ability to observe. This is already happening. Galaxies at the far edge of the observable universe are crossing the event horizon right now. Not quickly. Not in any way we could detect in a human lifetime. But over millions and billions of years, these galaxies are slipping away. The light we see from them is among the last light we will ever receive. Future photons they emit will not reach us. The galaxies are moving into a region of space from which no signal can ever escape to our location. And the process is accelerating. Because dark energy is accelerating the expansion. The rate at which galaxies cross the event horizon is increasing over time. More galaxies are leaving the reachable universe now than were leaving it 1 billion years ago. And more will leave in the future than are leaving now. The event horizon is not keeping pace with the expansion. It's falling behind. And the gap between what we can observe and what we can reach is widening. In the far future, billions of years from now, the observable universe will look very different. Most of the galaxies we can see today will have crossed the event horizon and faded from view. The universe will appear emptier, darker. The night sky will contain fewer galaxies, fewer clusters, fewer distant lights, not because those structures were destroyed, but because they moved beyond the boundary of observability. They still exist somewhere out there, continuing to evolve, forming stars, hosting planets, perhaps even supporting life. But they are no longer part of our cosmos. They are no longer part of the set of things we can observe, measure, or interact with. The event horizon defines the limit of your causal future. It tells you which parts of the universe you could, in principle, affect if you sent a signal now. Everything inside the event horizon is reachable. A photon sent today will eventually arrive there, given enough time. Everything outside the event horizon is unreachable. A photon sent today will never arrive. The signal will travel forever and never reach its destination. This is different from the particle horizon, which tells you about the past. The particle horizon grows as the universe ages, revealing more of the cosmos as light from further regions finally reaches us. The event horizon shrinks, in a sense. Not in physical size, but in content. Fewer and fewer galaxies remain inside it. More and more slip beyond it. The set of things you can reach is diminishing. And this process is irreversible. There is no technology that can overcome this. No method of travel, no form of propulsion, no manipulation of space-time that can allow you to reach a galaxy beyond the event horizon. The boundary is not a physical barrier. It's a geometric consequence of expansion. Space itself is the obstacle. And space is not something you can push aside or move through faster. You're embedded in it, subject to it. And when space expands faster than light can cross it, there is no escape. The event horizon is the ultimate edge of possibility. It defines not just what you can see, but what you can ever hope to influence, reach, or confirm. And it is closing in. Time does not heal this separation. It deepens it. In a static universe, waiting would help. A galaxy too distant to reach today might become reachable tomorrow, as light continues its journey and distances remain fixed. But this universe is not static. It is expanding, and the expansion is accelerating. Waiting does not bring distant galaxies closer, it pushes them further away. Consider a galaxy currently sitting just beyond the event horizon, 16 billion light-years away in moving distance. Right now, at this moment, if you sent a beam of light toward it, that light would never arrive. The expansion of space between here and there is too fast. The photon would spend eternity crossing an ever-widening gap. But the galaxy is close to the boundary. It only recently crossed the event horizon. You might think that if you wait, if the event horizon expands outward even slightly, the galaxy might slip back inside, becoming reachable again. But that will not happen. Because while the event horizon is expanding, the galaxy is receding faster. The space between here and there is growing at a rate determined by the Hubble constant and the acceleration driven by dark energy. And that rate exceeds the rate at which the event horizon expands. The galaxy is moving away from the boundary, not toward it. Every passing second increases the distance. Every passing year pushes it further into the unreachable region. This is true for every galaxy beyond the event horizon. They are not hovering near the boundary, waiting to be caught by its slow expansion. They are racing away from it. The gap between the edge of what you can reach and the location of these galaxies is growing. And as dark energy continues to dominate the universe, driving acceleration, that gap will grow faster. The galaxies are leaving, and they are leaving permanently. But the more disturbing realization is this: galaxies currently inside the event horizon, galaxies you could theoretically reach if you sent light toward them today, will not remain inside the event horizon forever. As expansion accelerates, the event horizon will eventually stop growing. It will reach a maximum size and remain there, fixed, while the universe continues expanding around it. And when that happens, galaxies will begin crossing the event horizon from the inside out. Galaxies you can reach today will become unreachable tomorrow. This is not a distant theoretical concern. This is happening now, slowly, on timescales too long for human observation, but inevitable nonetheless. A galaxy currently 15 billion light-years away is inside the event horizon. You could send light toward it today, and that light would eventually arrive billions of years in the future. But if you wait too long, if you hesitate, that galaxy will cross the boundary. It will move from reachable to unreachable, and once it crosses, no signal sent afterward will ever reach it. The universe is not giving you infinite time to make contact. It is imposing a deadline. Every galaxy has a window of opportunity, a period during which it remains within the event horizon, and signals can still reach it. That window is closing. For some galaxies it has already closed, for others it will close in the future, and for a shrinking number of galaxies the window is still open, but narrowing. In billions of years, the event horizon will have contracted in content so much that only the local group, our gravitational neighbourhood containing the Milky Way, Andromeda, and a few dozen smaller galaxies, will remain reachable. Everything else will have crossed the boundary. Every distant galaxy, every galaxy cluster, every large-scale structure beyond our local surroundings will be gone. Not destroyed, but removed from the set of things we can ever interact with. And even within the local group, not everything is safe. The galaxies in our neighbourhood are gravitationally bound to each other. Gravity holds them together, preventing expansion from tearing them apart. The Milky Way and Andromeda are moving toward each other, not away, because their mutual gravitational attraction is stronger than the local expansion of space. In a few billion years, they will collide and merge, forming a single large elliptical galaxy. This merged galaxy will be our future home, and it will remain reachable, held together by gravity. But galaxies just beyond the local group, galaxies in nearby clusters, will not remain reachable. They're too far away for gravity to hold them. Expansion will carry them off. They will cross the event horizon and disappear from our causal future. And as time passes, fewer and fewer structures will remain within reach. The observable universe will empty, the night sky will darken, and the merged remnant of the Milky Way and Andromeda will find itself alone, surrounded by an ever-increasing void. An observer in that future universe billions of years from now will look out into space and see almost nothing. A few nearby galaxies, if any, remain bound to the local group. And beyond that, darkness. No distant galaxies, no clusters, no large-scale structure. The cosmic web, the vast network of galaxies and voids that defines the current universe, will have disappeared from view, not because it was destroyed, but because it moved beyond the cosmological horizon and faded into invisibility. That observer will have no way to know that the universe was once filled with galaxies. They will see an empty cosmos and conclude reasonably that their galaxy is alone, that the universe consists of one galaxy surrounded by infinite empty space. They will have no evidence of the Big Bang, because the cosmic microwave background will have redshifted into undetectability. They will have no evidence of expansion, because there will be nothing distant enough to measure recession velocities against. They will be cosmologically isolated, cut off from the history and structure of the universe, living in an informational bubble that contains only their local environment. And this future is not unique to them. It is the future of every sufficiently isolated region of space. Every galaxy cluster, every gravitationally bound group will eventually find itself alone, surrounded by darkness, with no evidence that the rest of the universe exists. The cosmos will fragment into disconnected islands, each unable to see or communicate with the others, each existing in its own observable universe that overlaps with no one else's. This is the unreachable future. Not a future where the universe ends, but a future where the universe becomes unknowable, where observation is limited to such a small region that most of reality lies beyond detection, where the evidence of cosmic history fades away, leaving future observers with no way to reconstruct what happened, no way to understand where they came from, and no way to know that they are not alone. You live in a privileged moment, a time when the universe is still young enough and expansion is still slow enough that distant galaxies remain visible. You can see the cosmic microwave background. You can measure the Hubble constant. You can observe the large-scale structure of the cosmos and reconstruct the history of the Big Bang. Future observers will not have this luxury. They will inherit a universe stripped of evidence, isolated and dark. The galaxies are leaving, and they are taking the answers with them. A horizon is not just a visual limit, it is an information boundary. Beyond it you cannot see, but more fundamentally you cannot know. No signal crosses it. No measurement reaches you. No data, no light, no particle of any kind from beyond the horizon can interact with anything on this side. The horizon does not merely block observation, it severs causality. It creates a region of space about which you can learn nothing, confirm nothing, verify nothing. Information in physics is not abstract, it is physical. Information is carried by particles, by photons, by fields. When you observe something, you're receiving information that has travelled from the object to you. A photon leaves a distant star, crosses space, enters your telescope and deposits its energy into a detector. That interaction is information transfer. The photon carried data about the star, encoded in its wavelength, its direction, its polarization, and that data is now available to you. Without that photon, you would have no information about the star. You could theorize, you could guess, you could use indirect reasoning based on other observations, but you could not know. Knowledge requires information, and information requires a physical carrier, and if no carrier can reach you from a region of space, then that region is unknowable, not hidden, not obscured, fundamentally unknowable. The cosmological horizons we have discussed, the particle horizon and the event horizon, are information boundaries. They mark the limits of what you can know about the universe. Inside the particle horizon, information has reached you. You have data. You can observe, measure, and analyze. Outside the particle horizon, no information has arrived. You have no data. You can speculate, but you cannot verify. Inside the event horizon, information can still reach you in the future. A galaxy 15 billion light-years away inside the boundary will continue sending light toward you. That light will arrive, eventually, carrying information about the galaxy's state at the moment the light was emitted. You can wait for it. You can build telescopes to detect it. You can extract knowledge from it. Outside the event horizon, no future information will ever arrive. The galaxies there will never send you another photon. They are lost to you, informationally, forever. This is a stricter form of isolation than mere distance. Distance can be overcome with patience. If something is far away but the distance is fixed, you can wait for light to cross it. You can send a signal and wait for a reply. But when distance is growing faster than light can travel, patience does not help. Waiting does not bring the information closer, it pushes it further away. The gap between you and the source of information widens with every passing moment, and the information becomes more and more delayed, more and more redshifted until it stops arriving altogether. At that point, the region beyond the horizon becomes decoupled from your reality. It exists, presumably. The laws of physics suggest that space continues beyond the boundary, filled with galaxies and stars and perhaps life. But you cannot interact with it. You cannot send signals to it. You cannot receive signals from it. It is causally disconnected. It might as well be a separate universe, entirely divorced from yours, because no chain of cause and effect can link the two regions. This raises a philosophical problem. If something exists but cannot ever be observed, measured, or interacted with, does it meaningfully exist for you? Not in an abstract sense, not in the sense of whether it is real, but in the sense of whether it matters, whether it is part of your universe, the collection of things you can know about, care about, or be affected by. Physicists are cautious about this question. The usual answer is that yes, it exists. The universe does not end at the cosmological horizon. Space continues, galaxies continue. The laws of physics are the same everywhere, and there is no reason to think that reality stops at the edge of what you can observe. The horizon is a limit on you. not a limit on the universe. You are the one confined, not the cosmos. But this is an assumption, a reasonable one, supported by the consistency of physical laws and the homogeneity of the observable universe, but still an assumption, because you cannot verify it. You cannot check what lies beyond the horizon. You cannot confirm that space continues, that galaxies exist there, that the laws of physics hold. You believe it based on extrapolation, on the expectation that the universe does not care about your location and does not structure itself around your observational limits. But belief is not knowledge, and in a universe with horizons there is a growing separation between what you can believe and what you can know. You can believe the universe extends infinitely in all directions. You can believe there are trillions upon trillions of galaxies beyond the observable universe. You can believe those galaxies contain stars and planets, and perhaps civilizations, but you cannot know. The information that would confirm or deny those beliefs cannot reach you. It is trapped on the other side of the boundary. This creates a strange situation. The universe you can talk about meaningfully, the universe you can make scientific claims about, is smaller than the universe that exists. Potentially much smaller. If the universe is infinite, then the observable universe, the region within the particle horizon, is an infinitesimal fraction of the whole. Most of reality lies beyond your reach, beyond your knowledge, beyond any possible confirmation, and the situation is worsening. As expansion accelerates, the event horizon is closing in. The volume of space from which you can still receive future information is shrinking. Galaxies are crossing the boundary and becoming informationally isolated. The universe you can interact with, the universe that can send you signals and receive signals from you, is getting smaller. Not in absolute size, but in content. Fewer galaxies, fewer stars, fewer sources of information. In the distant future, the observable universe will contain almost nothing. Just the local group, or whatever gravitationally bound structure remains after the Milky Way and Andromeda merge. Everything else will have crossed the horizon and faded into darkness. Future observers will have access to far less information than you do. They will see a lonelier cosmos. They will have fewer sources of data. They will know less about the universe, not because they are less capable, but because the information is no longer available. This is informational decay. The universe is not losing information in the sense that data is being destroyed. The information still exists somewhere, encoded in the positions and states of particles in distant galaxies, but it is becoming inaccessible. The carriers that would bring that information to you, photons and gravitational waves and neutrinos, are being blocked by the geometry of expanding space-time. The horizon is cutting you off from the data, isolating you inside a bubble of knowability that is slowly contracting. You exist at a moment in cosmic history when the universe is still largely transparent, when distant galaxies are still visible, when the cosmic microwave background can still be detected, when the evidence of the Big Bang is still accessible. But this moment is temporary. This transparency is fading. The information boundaries are closing in, and future observers will inherit a universe that is informationally poorer, darker, and more isolated than the one you see today. The horizons are not just edges of space, they are edges of knowledge, and they are tightening. There is a loneliness built into the structure of the universe. Not the loneliness of being physically alone, though that may also be true, but the loneliness of being cut off, severed from context, stripped of the ability to see where you came from or understand your place in the larger whole. This is what awaits any sufficiently isolated observer in the far future. This is cosmological orphaning. An orphan is someone separated from their origin, someone who has lost connection to the past, to the lineage that produced them. In a cosmological sense, orphaning occurs when the evidence of cosmic history disappears, when the signals that would tell you about the Big Bang, about the early universe, about the formation of galaxies and the large-scale structure of space, fade beyond detectability, when you're left in a universe that contains no record of its own beginning. This is not hypothetical. This is the trajectory the universe is following. In 100 billion years, perhaps less, the cosmic microwave background will have redshifted into invisibility. The faint glow of radiation left over from the moment the universe became transparent, currently detectable in every direction, will be stretched to such long wavelengths that no instrument could distinguish it from the background noise of empty space. It will still exist technically, but it will be undetectable, and with it gone, the most direct evidence of the Big Bang will vanish. An observer in that future universe will look out at the sky and see no cosmic microwave background. They will have no way to measure the temperature of the early universe, no way to confirm that the universe was once hot and dense, no way to verify that there was a beginning at all. They will see their local galaxy, or the merged remnant of several galaxies bound together by gravity, surrounded by darkness, and from that observation alone, they will have no reason to conclude that the universe is expanding, that it had a beginning, or that it contains anything beyond their immediate surroundings. The distant galaxies will be gone too, not destroyed, but moved beyond the cosmological horizon, their light redshifted into nothingness, their images faded from view. The night sky will be empty, no galaxy clusters, no distant quasars, no faint smudges of light indicating the presence of other structures, just a few nearby stars, if any remain, and beyond them, void. Without distant galaxies, there is no way to measure the Hubble constant, no way to observe the redshift of light and calculate the expansion rate of space, no way to determine that the universe is growing. The observer will see a static cosmos, unchanging and isolated, with no evidence that it was ever different. They will have no data suggesting that galaxies were once closer together, that the universe was once smaller, that anything existed beyond their local environment. They will be orphaned from the knowledge of expansion, orphaned from the Big Bang, orphaned from the cosmic history that shaped everything around them. They will live in a universe that appears eternal and unchanging, unaware that it is neither, unaware that they are seeing only a tiny fragment of a much larger, much older, much more dynamic cosmos that has simply moved beyond their ability to detect. This is not a failure of observation. This is a structural feature of an accelerating universe. The evidence fades, the signals weaken, the information carriers redshift into undetectability, and eventually, the observable universe becomes so informationally sparse that reconstructing the true nature of the cosmos becomes impossible, not difficult, impossible. The data is gone. Consider what this means for science. Science relies on evidence, on observation and measurement, on the ability to test hypotheses against data collected from the universe. If the data is not available, science cannot proceed. An observer in the far future could propose the idea of a Big Bang. They could theorize that the universe had a beginning, that it was once hot and dense, that it has been expanding ever since. But they would have no way to test this theory, no cosmic microwave background to measure, no distant galaxies to observe, no redshift data to analyze. The theory would remain untestable, unfalsifiable, a speculation with no empirical support. They might even propose the correct model of cosmology, the exact sequence of events that actually occurred, and they would still have no way to confirm it. The universe would offer them no evidence, no clues, no signals that could distinguish the true history from an infinite number of alternative possibilities. They would be cosmologically blind, not because of any limitation in their instruments or their intellect, but because the universe has evolved to a state where the evidence no longer exists. This orphaning is gradual. It does not happen all at once. The galaxies do not disappear overnight. The cosmic microwave background does not vanish in a single moment. The process unfolds over billions of years, slowly eroding the observational foundation on which cosmology is built. Each passing eon removes a little more evidence. Each galaxy that crosses the horizon takes with it a piece of the puzzle, and eventually so many pieces are missing that the puzzle can no longer be solved. We are living in a brief window, a cosmological moment when the universe is old enough to have developed structure, galaxies, stars, and perhaps observers, but young enough that the evidence of its history is still accessible. We can see the cosmic microwave background, we can measure the expansion rate, we can observe distant galaxies and trace the evolution of cosmic structure over time. We can reconstruct the Big Bang, estimate the age of the universe, and map the distribution of matter across billions of light years. But this window is closing. The evidence is fading. The universe is moving toward a state where such observations will no longer be possible, where the data will be gone, where future observers will be orphaned from the knowledge we take for granted. They will inherit a cosmos that appears simple and small and unchanging, unaware that it is vast and ancient and dynamic, because the information that would tell them otherwise will have redshifted beyond recovery. This raises an uncomfortable question. If future observers will be orphaned from cosmic history, unable to access the evidence that would reveal the true nature of the universe, are we also orphaned? Are there features of the universe, events in its past, structures beyond our horizon that have already faded from view? Information that was once accessible but is now lost, red-shifted into invisibility before we were here to observe it? The answer is almost certainly yes. The universe is older than the observable universe is wide. There has been time for light to travel only a finite distance. Regions of space that are now beyond the particle horizon were once within it, closer to us, their light reaching us in the early universe. But as expansion accelerated, those regions moved beyond the boundary. Their light stopped arriving, and any information they contained about the very earliest moments of cosmic history is now lost to us. We are seeing the universe as it was within a certain range of time, not the very beginning, because the universe was opaque in its earliest moments and no light from that era can reach us, and not the very edge of what exists, because regions too far away have not had time to send us light yet, or have already moved beyond the horizon. We are seeing a middle range, a window in time and space, and we are orphaned from everything outside that window. We do not know what we are missing. We cannot know. The information is not here. It never arrived. Or it arrived and was lost, or it exists somewhere beyond the horizon, forever out of reach. We are working with incomplete data, constructing a picture of the universe from the fragments we can access, aware that the full picture is larger but unable to see how much larger or what it contains. And the fragments we do have are disappearing. The window is narrowing. The orphaning is deepening. Future generations will have less data than we do. They will see fewer galaxies, detect fewer signals, have access to fewer pieces of evidence. They will be more isolated, more cut off, more alone in a darkening cosmos that offers them less and less information about itself. This is the trajectory. This is the future. Not an ending, but a fading. A slow withdrawal of the universe from view, leaving behind only the closest structures, the gravitationally bound remnants of what was once a vast and interconnected web of galaxies. Everything else will be gone, not destroyed, just removed, placed beyond the boundary of knowability, and those who remain will be orphaned from the cosmos. You have always lived inside a bubble. You were born inside it. You will die inside it. Every human who has ever existed, every observation ever made, every measurement ever recorded has occurred within this bubble. It is not a physical structure. There are no walls, no membrane, no surface you could touch or detect. But the bubble is real. It defines the limits of your reality. Everything inside it is knowable. Everything outside it is not. The bubble is the observable universe, the sphere of space, roughly 93 billion light-years in diameter, from which light and information have had time to reach you since the beginning. This is your cosmological prison, not a punishment, not a constraint imposed by anyone or anything, simply a consequence of finite age and finite speed. Light travels at 300,000 kilometers per second. The universe is 13.8 billion years old. These two facts, combined with the expansion of space, define the size of the bubble. Inside the bubble you have access. You can observe galaxies, detect radiation, measure distances, analyze light. You can study the cosmic microwave background, map the distribution of matter, trace the history of structure formation. You can test theories, make predictions, confirm or reject hypotheses. Science functions inside the bubble because the data is here. The information has arrived. The universe within the bubble is observable, knowable, subject to investigation. Outside the bubble you have nothing. No data, no signals, no information. The universe beyond the bubble may be infinite. It may contain trillions upon trillions of galaxies, each with billions of stars, each potentially hosting planets and life and civilizations. Or it may be empty, or it may be structured in ways entirely different from what you observe inside the bubble. You cannot know. The information that would tell you has not reached you, and in many cases it never will. This bubble is your entire empirical universe. Not the universe itself, but the portion of it you can interact with. The rest, the vast unknown beyond the horizon, exists only as theory, as extrapolation, as an assumption that the laws of physics you observe here apply everywhere, that the universe does not end at the edge of observability, that space continues beyond the boundary. These are reasonable assumptions, but they are not facts. They are beliefs, held because they are consistent with everything you have observed, but not provable, not testable, not confirmable. And the bubble is not static. It changes. It evolves. In the early universe, the bubble was smaller. Fewer regions had had time to send light to what would eventually become your location. As the universe aged, the bubble grew. More light arrived. More regions came into view. The observable universe expanded, incorporating new galaxies, new structures, new information. For most of cosmic history, the bubble has been growing, slowly revealing more of the cosmos. But the growth is slowing, and in some sense, it is reversing. The particle horizon, the edge of what you can currently see, is still expanding. Light from further regions is still arriving. But the event horizon, the edge of what you can ever interact with, is approaching its maximum size, and galaxies are crossing that boundary, moving from reachable to unreachable, from observable to eventually unobservable. The bubble is losing content, not shrinking in size but emptying, becoming less populated, fewer galaxies, fewer sources of light, fewer pieces of the cosmos accessible to you. In the far future, the bubble will contain almost nothing. The local group, or whatever structure remains after gravitational mergers, will be all that is left. A single island of stars and gas surrounded by darkness. The bubble will still exist, still extend outward for billions of light years, but it will be empty. No distant galaxies, no cosmic microwave background, no large-scale structure, just void. This future bubble will be informationally dead. It will offer no data about the universe beyond itself. An observer inside it will see only their local environment and will have no evidence that anything else exists. They will be trapped inside the bubble, not by walls, but by the absence of information. They will be unable to learn about the wider cosmos because the wider cosmos will have stopped sending signals. But even now, even in this era when the bubble is still relatively full, you are trapped. The bubble defines the limits of what you can verify. You can theorize about what lies beyond it. You can use mathematics to extrapolate, to extend the known laws of physics into unknown regions. You can propose models of the universe that include vast expanses beyond the observable horizon. But you cannot test those models. You cannot check whether your extrapolations are correct. You cannot confirm that the universe beyond the bubble resembles the universe within it. This is a fundamental epistemic limit. There are things you can know and things you cannot know, and the boundary between them is the edge of the bubble. Inside, knowledge is possible. Observation provides evidence. Theories can be tested. Outside, knowledge is impossible. Observation provides nothing. Theories remain speculative, forever untestable, no matter how reasonable they seem. And the bubble is subjective. It is centered on you, or more precisely, it is centered on your location in space and time. Every point in the universe has its own bubble, its own observable universe, its own horizon. An observer in a galaxy 10 billion light-years away has a different bubble. It overlaps with yours, but it is not identical. There are regions of space visible to them that are not visible to you, and vice versa. Their particle horizon is in a different location. Their event horizon encompasses different galaxies. They live in a different empirical universe. This means there is no single, universal observable universe. There are countless overlapping bubbles, each defining a different collection of knowable facts, each limiting a different observer in different ways. The universe as a whole, the totality of everything that exists, is not observable by anyone. Every observer sees only a fragment, a local piece, a bubble centered on themselves, and these bubbles do not communicate perfectly. If you and the distant observer both look at a galaxy that lies in the overlap between your two bubbles, you will see it at different times in its history. You will see the light it emitted when it was a certain distance from you. They will see the light it emitted when it was a different distance from them. You're both observing the same object, but you're seeing different moments in its evolution, different states, different configurations. The galaxy has no single appearance. It has a history, and different observers see different parts of that history. This fragments reality, not into separate universes, but into separate perspectives, each valid, each incomplete, each unable to access the full picture. You can never see the galaxy as it is now. You can only see it as it was when the light left it, and by the time the light arrives, the galaxy has moved on, it has evolved, it has changed. The image you receive is outdated, delayed. A historical record, not a live view. The bubble enforces this delay. It enforces incompleteness. It ensures that no observer can have a complete, up-to-date picture of the universe. Everyone is working with partial information. Everyone is seeing fragments of the past. Everyone is trapped inside their own local bubble, limited by the speed of light and the expansion of space. And the bubble is closing. The event horizon is tightening. The volume of space you can interact with is shrinking. The number of galaxies you can reach is decreasing. The amount of information available to you is diminishing. The bubble is becoming more isolated, more cut off, more alone. You exist inside this bubble now. Everything you know, everything you have observed, everything you can confirm is inside it, and you will never leave. You will never see beyond the horizon. You will never know what lies in the unreachable regions of space. You will never confirm whether the universe is infinite, whether it contains other structures beyond your view, whether the laws of physics hold everywhere, or only within the small fragment you can observe. The bubble is your universe, not the universe, but yours. The only one you will ever have access to, the only one you can ever know. There is a question you cannot answer. It sits at the edge of every cosmological observation, every measurement, every theory about the structure of the universe. The question is simple. What lies beyond the horizon? You know what lies within it. You have mapped the observable universe. You have catalogued galaxies, measured distances, traced the distribution of matter across billions of light years. You have observed the cosmic microwave background, analysed its fluctuations, extracted information about the density and composition of the early universe. You have built a detailed picture of the cosmos within your reach. But beyond the horizon, you have nothing. No data, no observations, no evidence. The horizon is an absolute barrier to knowledge, not a temporary obstacle that better technology might overcome, but a permanent limit imposed by the geometry of space-time. Light from beyond the horizon has not had time to reach you. It will never reach you. No signal, no particle, no wave of any kind can cross the boundary and deliver information about what lies on the other side. The regions beyond the horizon are causally disconnected from you. They might as well exist in a separate universe, but they do not exist in a separate universe. They are part of this universe. The same space-time that contains the observable universe extends beyond it. The laws of physics do not stop at the horizon. Space does not end there. The most reasonable assumption, the one supported by the uniformity and isotropy of everything you can observe, is that the universe continues, that it extends beyond the bubble, that it contains more galaxies, more stars, more structure, continuing outward in all directions, perhaps infinitely. This assumption is foundational to modern cosmology. The cosmological principle states that the universe is homogeneous and isotropic on large scales. Homogeneous means it has the same properties everywhere. Isotropic means it looks the same in all directions. If this principle holds, then the universe beyond the horizon should resemble the universe within it. The same kinds of galaxies, the same distribution of matter, the same physical laws. Nothing special about our location, nothing unique about the region we happen to occupy. But this is an extrapolation, a projection of what you observe here into regions you cannot observe. It is supported by the fact that everywhere you look within the observable universe, you see roughly the same thing, the same kinds of structures, the same expansion rate, the same physical constants. This suggests that the universe is uniform, that it does not have special regions or preferred locations, that what you see here is representative of what exists everywhere. But you cannot prove this. You cannot check. The regions beyond the horizon are invisible, unreachable, forever beyond confirmation. You can assume they are similar to what you observe here, and that assumption is reasonable, but it is not knowledge. It is belief, and belief, no matter how well founded, is not the same as verification, and there are scenarios where the cosmological principle might not hold, where the universe beyond the horizon is different from the universe within it, not because the laws of physics change, but because the universe is larger and more complex than the region you can see. If the universe is infinite, then it contains infinite variation. Every possible configuration of matter, every possible structure, every possible history occurs somewhere. The observable universe is a finite sample of an infinite whole, and a finite sample, no matter how large, cannot capture all the variation that exists. In an infinite universe, There could be regions where galaxies are more densely packed, regions where they are sparser, regions where the initial conditions were different, leading to different evolutionary paths, regions where the constants of physics vary slightly, producing different kinds of stars, different kinds of chemistry, different kinds of complexity. All of this could exist beyond the horizon, invisible to you, undetectable by any means, but real nonetheless. Or the universe could be structured on scales larger than the observable universe. The cosmic web you observe, the network of galaxy clusters and voids, could be a small piece of a much larger pattern, a pattern that repeats, or evolves, or changes in ways that are only apparent when viewed from a scale far exceeding the size of the bubble. You would have no way to detect this, no way to know whether the structures you observe are local fluctuations in a larger order or representative of the universe as a whole. Or the universe could be fundamentally different beyond the horizon, not in its laws but in its history. Different regions of space could have undergone different inflationary epochs, producing different expansion rates, different densities, different outcomes. The observable universe could be one bubble among many, each with slightly different properties, each causally disconnected from the others, each evolving independently. You would see only your bubble. The others would be beyond your reach, beyond your horizon, beyond any possibility of observation. These are not idle speculations. They are possibilities allowed by the physics you know. Inflation, the rapid expansion of space in the very early universe, can produce a multiverse, a collection of causally disconnected regions, each with its own observable universe, each potentially differing in initial conditions or physical constants. If this is true, then the question of what lies beyond the horizon becomes even more profound. Because the answer might not be more of the same, it might be something entirely different. But you will never know. The horizon prevents you from checking. It seals you inside the bubble and leaves the question unanswered. You can propose theories. You can build models. You can argue about which scenario is most likely based on indirect reasoning and theoretical consistency. But you cannot observe. You cannot measure. You cannot confirm. This creates a strange situation for science. Science is built on the principle that claims must be testable, that theories must make predictions that can be checked against observation, that knowledge comes from evidence, not from speculation. But the regions beyond the horizon are inherently untestable. No observation can ever access them. No experiment can ever probe them. They lie permanently outside the domain of empirical science. Does this mean they are not part of reality? Not in any practical sense. They exist, presumably, whether you can observe them or not. The universe does not care about your observational limits. It does not structure itself around what you can see. But from the perspective of science, from the perspective of what you can know and verify, the regions beyond the horizon are effectively non-existent. They do not contribute to your empirical universe. They do not affect any measurement you could make. They are, in every operational sense, irrelevant. And yet, they might be vast. If the universe is infinite, then the observable universe is infinitesimally small compared to the whole. Most of reality lies beyond the horizon. Most of existence is unknowable. You're confined to a tiny bubble, a minuscule fraction of the totality, with no access to the rest. This is the final edge. Not the edge of space, but the edge of knowability. The boundary between what you can investigate and what you cannot. Between the empirical and the speculative. Between the universe as it appears to you and the universe as it might actually be. And this boundary is absolute. You cannot cross it. You cannot extend it. You cannot overcome it with technology or ingenuity or time. The question of what lies beyond the horizon will remain unanswered, not because it is too difficult, but because it is unanswerable. The information does not exist here. It cannot reach you. It is sealed on the other side of a barrier that nothing can cross, and so the question sits there, at the edge of every cosmological theory, every map of the universe, every attempt to understand the whole, a question without an answer, a boundary without a crossing, an edge where everything you can know ends and everything you cannot begins. The edge is not a place. You cannot travel to it. You cannot point to it on a map and say, there, that is where the universe ends, because the universe does not end. Space continues. Matter continues. The laws of physics hold. What ends is not the cosmos, but your relationship with it, your ability to see it, to reach it, to know it. You exist inside a sphere of light. Everything you have ever observed, every galaxy and every photograph, every distant signal, every ancient photon lies within this sphere. It is roughly 93 billion light-years across, expanding slowly as the universe ages, incorporating new regions as light from further distances finally arrives. But the sphere is not growing fast enough. The universe beyond it is receding faster than the sphere can expand. Galaxies are slipping beyond the boundary. Information is fading. The cosmos is withdrawing from view. This is not a failure. It is not something broken or wrong. It is simply the consequence of living in an expanding universe with a finite age and a finite speed of light. The edge is built into the structure of space-time itself. It is a horizon, not a wall, a limit of causality, not a boundary of existence, and it is closing in. In the far future, the sphere will be almost empty. The galaxies you can see today will have faded into darkness. The cosmic microwave background will have redshifted beyond detection. The evidence of the Big Bang will be gone. Future observers will inherit a lonelier cosmos, one that offers them fewer clues, fewer signals, fewer pieces of the puzzle. They will be orphaned from the knowledge you take for granted. They will look out into an empty sky and see nothing but their local surroundings, unaware that the universe was once filled with light. But you are here now. You exist in a moment when the universe is still visible, when distant galaxies are still detectable, when the history of the cosmos is still accessible. You can see the edge even if you cannot cross it. You can measure the horizon even if you cannot reach it. You can know that there is more beyond even if you cannot observe it. This makes you small, not in a diminishing way, but in a clarifying way. You're confined to a bubble of knowability, a tiny region of space and time within a cosmos that is vastly larger, possibly infinite, and mostly beyond your reach. Most of reality is invisible to you. Most of existence is unknowable. You occupy a fragment, and the fragment is all you will ever have. And yet, within this fragment, you have built understanding. You have mapped the stars. You have traced the expansion of space. You have reconstructed the history of the universe from the light that reaches you. You have taken the limited information available inside the bubble and used it to understand how the cosmos works, how it began, how it evolves. You have turned observation into knowledge. You have made meaning from the signals. This is not nothing. It is everything you can do. You cannot escape the bubble. You cannot see beyond the horizon. You cannot overcome the limits imposed by light and time and expansion. But you can understand those limits. You can recognize them. You can acknowledge that the universe is larger than what you see, and that your place within it is small and temporary and confined. The edge is where everything ends, not the universe, but your access to it. Not existence, but knowability. Not reality, but the portion of reality you can interact with. And beyond that edge, the cosmos continues, indifferent to your inability to observe it, indifferent to your questions, indifferent to your existence. It simply is. Vast. Mostly hidden. Forever out of reach. You stand inside the bubble, looking outward, knowing there is more but unable to see it. And that is where you will always stand. At the edge of the knowable. At the boundary of light. At the limit of what the universe will ever show you. Small but aware, confined but conscious, trapped inside a sphere of visibility that defines all you can ever know about the cosmos and all the cosmos will ever reveal to you. This is the edge, and this is where you remain.